Good afternoon, everyone. Let's catch up from the last discussion. So, if you see in the last discussion, we were primarily discussing how the wave is propagating through a medium, and if we are and we try to look at how we are writing the wave equation, and yes, so how we are writing the wave equation. We have also shows the temporal frequency, spatial frequency, and as well as we have shown in a periodic structure how one point is correlated with the previous and next units of it in the same location. How we can able to correlate? We have finally seen that the displacement of the similar location can be expressed from the wave number, and there actually the temporal frequency terms drops, and that is formally known as the Bloch theorem. Now if we are implementing that Bloch theorem into the equilibrium of the structure, we can able to solve and we can able to derive the dispersion relationship, and that dispersion relationship is actually the correlation between the wave number and the temporal frequency. And we have seen very interesting point that once we are giving a frequency to the structure, then wave number can be real, can be imaginary, purely imaginary, and can be a complex number. Because you can see here, and based on that we can get, and we try to also interpret that what is the meaning of a real wave number, complex wave number, and purely imaginary wave number. We have also seen that how the space is actually look like, and we have also discussed that these things are quite resembled with the damped vibration, response of the damped vibration, response of the critical or over damped system and under damped system, and but in those cases it is varying with time, whereas here it is varying with space. That's the prime difference between these things. Any question up to that? Any question in the from the previous class? Okay, if no, then we can let's proceed further. So we got up to that stage. Okay, so we can see that once so we have given a particular, so in this case, so in the last class we have seen that we have given a particular value of omega, and from there we try to calculate what is the kappa. Okay, and up to few classes we will restrict ourselves that we are giving omega and we try to calculate the kappa. So, and we also started discussing, assuming that, like, let's say someone is went to the gym holding a gym rope and like waving his hand, so that a wave is propagating in the gym rope. Okay, now if you think, we see in the last case that once the omega is less than equal to root over of 2k by m, like you see here, so omega less than equal to root over of k by m, and that, so once this thing is happening, that omega is less than equal to 2 into root over of k by m, the wave will propagate. That means what? If we have that gym rope, we are exciting it to slowly, omega is less, wave will propagate. But once we increase the frequency and once we cross that, then what will happen? So in that case, what happened? The kappa belong to a real, and wave will propagate. because we will get a solution that it is alpha and we can able to get it like that. And what is the medium equation become? Medium equation is becoming means x of t. So if I'm just forgetting something like that is something like y of t into e to the power of minus I alpha x, which is nothing but y of t into cos of alpha x minus I sine alpha x. So we can able to see the wave is propagating in that medium when the frequency is within that limit. Now frequency exceeds, you become so energetic, you thought, okay, why not, we'll do it very fast, and you started looking that wave is no longer propagating. Why this will happen? Now once your frequency is more than, then what will happen? Then k will have in two part, alpha plus I beta, and your solution, you can see that it will start decaying. So you hold the gym rope, you try to do it, but you see you do it, but wave is not propagating, it is decaying because you are doing it too fast. Now here, if you try to notice, you can understand where this wave propagation concept is much more in depth compared to the structural dynamics, because in structural dynamics what we can see, or like once we are talking only the vibrations, what we can see, we are looking that okay, we are giving the excitation, fine, that point is moving, but after that inside the space that complete vibration get attenuated, and that information we can easily able to capture very nicely in this full thing. You got that? Is it clear? Is it clear? Perfect. So now, so like next time maybe if it not seems like people are going to gym, I am also not going to gym, but but suppose if you guys are going to gym sometime next, then that time maybe you can try to feel or do that way, that okay, excite it like a proper excitation so that it can able to propagate. So you can understand that if you just do it, it will not going to propagate. Okay, nice. Another very interesting point, if you think that once we start solving the full theme, what was our assumed solution? Y of x comma t equal to agreed? That was my assumed solution. Now we see that some of the cases wave will propagate, some of the cases wave will not propagate. So for all the cases, does that solution valid or not? What do you feel? So you have seen for some omega, kappa is not real and wave is not propagating. So fundamental question, we assumed, we started solving it assuming that the wave is propagating. We write the equation of motion from that aspect. Does that very fundamental equation holds after that finding? Yes or no? Question is very simple. That does the equation holds or not? We assumed it that wave will propagate. We found that wave is not propagating. Does my equation, first equation, what I assumed, still holds correct, or we need to modify it? That's the only question. Modify it. Okay. How many of you feel that we need to modify? Maybe the best question is how many does not have any clue. So think. It seems like we need to modify, but it's not required to modify. We have already seen what? If the kappa value is becoming complex, it will take care of the dissipated condition. I am not saying that this in this equation that kappa is real. I am not saying that. I am not saying that. If I would have said that, it was wrong. I just said that is kappa. I did not say, I did not restrict that kappa is real. I am not saying that. If kappa is complex, automatically that gives that decay solution. So what's the problem? Kappa can be complex. Agreed. So it does not require to change the solution. It is or does not require to change the assumption. I mean, yeah, assumed solution. Yeah, assumed solution is still fine because we are not restricting anything. We just make it liberal that okay, if it is, and rather you can say we make it much more clearer that if kappa is real, wave will propagate. If kappa is imaginary, wave will clearly decay. If kappa is complex, it will decay with oscillations. Very clear, no problem at all. Perfect, good. So like this way we can able to get that. Now here there is one important point I need to mention, that is often you will found that equations are written in the different manner. Like I started with this way. That I started in teaching. People may also write, this is not equal, means I'm just saying the different ways of writing. So people may also write it omega t minus kx. May also often people write it several different things are possible. People often sometimes do not put the I with kappa. Now if they do not put I with kappa, then you need to understand there will be a difference. What I wrote, that kappa equal to, in previous case, I beta, and if beta is equal to 0, kappa will be real and wave will propagate. Okay, that is for the first, second cases. That is for first and second case. Okay, but for third case, in that case, if alpha is equal to 0, then kappa, then wave will propagate. Because now if you substitute it here, I will be associated with alpha. I mean, sorry, I will be associated with beta, not with alpha. So that point you need to be very careful. If somebody writes the equation in the opposite way, you need to check and you need to find out the coefficients accordingly. Okay, make sense? Yes. Now another important point we have seen in the last case, once we were doing that, beta not equal to 0 case can be decay and can be growth. So if I try to plot it clearly, like if I think that other case beta, I mean, suppose I am writing it like sorry, so much over writing. Y equal to a e to the power of minus I omega t plus kx. So here kappa equal to alpha plus I beta and beta not equal to 0. So in that case, what is happening here? Going like that. Okay. Now if you think this is your first unit, this is your second unit, this is your third unit, that will become a crazy thing because wave amplitude will grow. So that's not correct. It should be always like this. Okay, that wave amplitude can only decay, it cannot grow. If you are getting a beta value positive, that means you have to understand wave is going to the opposite side. Okay, you think wave is going to the opposite side, then you will get it negative. Make sense? Because you cannot get growth wave. Wave cannot grow. Wave can decay. Means wave can grow if there is some additional source of excitation. But in normal cases, just if you assume a equation, full system is like a normal, like no additional source or energy sources or something is not there, wave cannot go. So that thing is not correct. So you have to, if you get this type of solution, you should understand there is some mistake somewhere, you should avoid it and you should just straight go. Okay, clear? Nice. Yes, so this point up to that is done. Now let's see about the solution what we got, and that is basically the dispersion relation what we got. So what we got there, yes, so my equation was this one. So that is my dispersion relation. I can just start it from another page. So what is dispersion relationship? Dispersion relationship is basically a relation between the wave number and the frequency. Okay. So for the monoatomic chain, it is minus omega square m plus 2k into 1 minus cos kappa a, that is equal to 0. Okay. Now let's see a little bit more. Now let me introduce a term instead of kappa into a. So okay, so now if I try to see what are the units of this parameter, let's go back and try to check what are the units of this. So what is the unit of omega? Radian per second. Okay. What is the unit of kappa? Meter inverse, 1 by meter. Why? Exactly. As per the dimensional theory, once we are having this type of term, that should be dimensionally consistent. Now one has second, s means that t is obviously second and x is obviously meter, or means the dimensionally if I say x is, means that t is like capital T and x is capital L, the dimension. So definitely that should be nullified. So there should be inverse of that. So definitely, and radian has no unit. So this is, and instead of omega it can be f also 1 by 7. Both the things are fine, but omega is radian per second, that is correct. So we are having this thing. So here now if you think, once we are having that, now often we write it that kappa times a, that is what should be the unit of it? A is what? Length between the units, so it is length, and kappa is 1 by length, so kappa times a is dimensionless. So often people call it as mu. Okay, and the front portion also sometime written as now. What is the k by m? Anybody? K is the stiffness divided by mass, that is equal to natural frequency. So that is also some sort of like frequency. We can call it like maybe omega n. Okay. So what can I get it at the omega square? So I am getting it omega by omega n square plus 2 times 1 minus cos nu, and now I can call it omega by omega n, that is equal to eta. Again another non-dimensional parameter I am introducing here. So I can call it eta square plus 2 into 1 minus cos mu, that is equal to 0. So 2 into 1 minus cos mu, that is equal to eta square. So 1 minus cos mu equal to eta square over 2. So cos mu equal to 1 minus eta square over 2, and okay, can I write it like this way? Or instead it can also be written in another way. That is, what is 1 minus, so what is cos 2 theta? 1 minus 2 sin square theta. So what can I write? Cos mu equal to 1 minus 2 sin square mu by 2. So 2 sin square mu by 2 equal to 1 minus cos mu. So can I write 2 sin square mu by 2 will be equal to eta square by 2? Can I say that? So sin square mu by 2 will be equal to eta by 2 whole square. And now if we try to plot the thing, we are giving eta and we try to plot mean. What can we get? Sin square mu by 2 equal to eta square. So how it should look like? If somebody just normally plot in the opposite way, let's say, just let me just do it opposite first. So if somebody plot it in the opposite way, we put first mu eta Nothing. Like this way they will get. So this is mu. This is mu, means wave number, and this is eta. Or if I draw it that way, why this fancy type of things is happening? You may be feeling it so odd, drawing so oddly, but why this thing is happening? Anybody? Exactly. It is only positive. Yeah, that is one case. As well as you can see, that is like, and also you have to understand this way. Once we are plotting, it is something like taking the consideration that our mu, or sorry, eta, is not crossing the value where mu becomes complex. You see, there is a very clear boundary exists. Why that boundary exists? Because what is the limit of the sine square mu by 2? When that mu will become complex. What is the range? The range of sine is always -1 to 1. What will be the range of sine square? 0 to 1. So simple. So this value cannot cross more than 1. If it crosses more than 1, it will become like it cannot be, means actually coming. Yeah. So that value will become then imaginary. So this type of graphs will come. And importantly, what if you see mu several values we are getting. So what we can say, for a particular value of eta, like let's say we tell it that eta a particular single value, we will get several value of mu. Why? Because it can have a general solution. It is sine. It is sine. So once we are putting the sine, cosine, this type of function, it can give us the general solution of that. It is not a single solution, it's a general solution. So once the general solutions are coming, definitely the because if you think it will become how? Equal to plus minus eta by 2. Okay. So once it is plus minus eta by 2, that thing is happen, and eta is not negative. So this way this thing will actually come, and we will get it in the negative side also. Now another important point is that, so this is the diagram happens, but here it seems like we are varying what? Mu, not varying eta. But our prime objective was to vary eta, not to vary mu. So this is actually the general solution of mu with, or you can say that real solution of mu with respect to real value of the eta. So here it is showing where the wave is propagating. If we are taking a propagating wave, what should be the value of eta and what should be the value of mu? Here no complex, no decay, no attenuation of the wave exists. Clear? It is just purely propagation case. In propagation case, what should be the correlation between these two things? Okay? Agreed? Both of you? Now, if we try to draw a simpler version of it, we can simply say that this is my eta axis, this is my mu axis, my solution will go up and end like this. And what should be the value of this value of the mu? Think. Here, what should be the value of mu? What should be this value? Please tell anybody. Where the graph will turn? When sin mu will reach to maximum value. So what should be the maximum value? 1. Exactly. So if it is reaching to 1, what should be the value of mu? So mu by 2 is so sin mu by 2 is equal to sin pi by 2. So what should be mu? Pi. So this value is pi. Okay. And what should be the value of eta? One. Think. If your mu is pi, then this has become sin pi by 2. That is 1. So mu equal to 2. Is 2. And this is pi. Got that point? All of you agree with me? So now, if you see in what practically means, so if you are going this one, this is like repeating the different mu, that also make no sense. Like you are having a general solution, but do not go into that complexity, because those things, yeah, it's true that the general solution is coming, but does that really required for our case? It's not. So we don't need to unnecessarily thought about the general solution. Rather, focus on the first solution, and that first solution will give us simple this curve. Is clear? We are reaching up to mu, but here, so we're reaching up to mu, and we can see that up to eta value 2, we can able to get a real wave propagation. What about after that? That's something, a question. There, mu become imaginary. Okay? And additionally, here this thing has its significance in the physical, I mean from the physics point of view, that is like Brownian zone and all those things people are defining. Like for example, if you think this to this region is known as the first Brownian zone, then this region to this region is known as the second Brownian zone. Like this way, that Brownian zone concept is comes. But if we forget those things, if we just think it in a very simplistic mechanics way, then we don't need to go into that deep, and we can think that okay, we are getting this. Now the more interesting point comes, what will happen if we are getting the complex side. So we already see the real portion, and we say that eta is 2, up to 2 we are getting a real value. Now eta can be more than 2, because what is eta? Eta is omega by omega n. So whatever is the natural frequency, or not natural frequency, that is root over of, means the k by m. So once we are crossing that k by m 2 times, then we start something different. So what will happen in that case? So now let's see how the solution should come. We will have this solution or this solution. So if you solve that further, you can see, and now you are plotting it little differently. So I'm just plotting the real part of the mu here and imaginary part of the mu at the bottom side. Okay, because actually what is happening, you will have both the mu value plus and minus, but minus value shows what? Wave is going in the opposite direction, and as the lattice is reciprocal symmetric type of lattice, both the waves should go in the similar manner. I don't need to plot unnecessarily both the things. Okay, so what can we do? Rather, we just assign the top part as like a real of mu and bottom part as the imaginary of mu. So this is known as the folded version of the dispersion diagram. So this is the folded dispersion plot. Folded dispersion. Previous one is the unfolded dispersion plot. All the mu's we are looking at, like it's a full general solution, like this way it is coming. But in unfolded, we do not have the complex part. That is also important thing. In the folded, we can have the complex part as well. Now here what happened? We are plotting the complex. So you can see that the complex part will coming like this way. The complex part will go like this. If we solve that and plot the complex part as well, we can see that it will go in this fashion. Okay. So now here one very interesting point, and we can also able to see that with this imaginary part of the mu, that means beta, we will not get any real part of the mu. Means the real mu and imaginary mu means what? If the mu is alpha plus I beta, then real mu is alpha and imaginary mu is beta. Make sense? So if you think that imaginary mu is getting higher, that means what? That means what? You are having y of x, that is equal to y into e to the power of minus beta x, if you think. So that beta is increasing. That means what? That was like beta 1. This one will be beta 2. Here beta is increasing. Beta increasing means you will get the decay much faster. Within very small amount of displacement, you will get the much quicker decay. Got it? Think very similarly in the damped vibration. If your damping increased, what will happen? You will get faster decay in time domain, higher damping, faster decay, higher beta, faster dissipation in the spatial domain. Got it? Clear? Done. This is good. So this is primarily, I'm forgetting. No, nothing. Okay, no issue. Yes, we got that. Okay, we got that thing. Now let's do another way of calculating the dispersion relation. We will just do that and we will stop today's class, because that will complete the monoatomic case fully. And then from the next class, we will start doing the diatomic and so on. We will go. Okay, so okay, before I jumped into any doubt up to that. Anybody? Any doubt? No doubt. Good. That's simple thing, not that difficult. Okay. So now, if you think, now let's say mass m, stiffness k, all the distance a. Okay. So somebody gives you a chain having the mass m, having the stiffness k, and asked you to calculate the dispersion relationship. What should be the right way or right approach, or the different approaches to solve that problem? Let's discuss on that. Okay. So there are primarily two ways what we can do. First thing, we can implement the Bloch theorem. Okay, so if we implement the Bloch theorem at the very first place, the way we have just solved. So let's assume this is my y1, this is y0, this is y2. I can write y2 equal to y1 e to the power of minus I kappa a, and y0 equal to y1 e to the power of I kappa a. Okay. Okay. Agreed, all of you? So I apply the Bloch theorem twice in the displacement field. Okay, this is the displacement field. I applied it twice and I try to write the equation of motion as like if I substitute everything here, and also if I write y1 equal to y1 double dot equal to minus omega square y1, I can able to get the dispersion relationship. I have just done that in the last class. Agreed, all of you? That way we can able to get that. That is one approach. But if you see here, periodicity concept came or not came? Anybody? Periodicity concept came to some extent. You can say that periodicity concept came where now a value we are substituting, and there the periodicity concept came. Yes, so we are using 2 times the Bloch theorem here. Now another important point can be thought of by making the unit cell. You may be heard, or if you are studying the metamaterial, you may heard the term that we can also able to get the dispersion relationship from the unit cell of the structure. Now if we can able to get it, then first thing is that we have to construct what is the unit cell of that full thing. Okay, so I'm not going first that exact definition of the unit cell. Exact definition of the unit cell we will do once we are studying the 2D wave propagation. But if we are thinking normally that unit cell means we need to find out a repetition pattern which is repeating the full structure, and with that repetition we can able to get that full chain. We can recreate the full chain. Okay, so I can able to take this portion, that dotted part, take it, repeat it. I should able to get my main structure. I can cut that mass half. I can repeat it. I can cut the mass with any proportion. I can repeat it and I will get that. Okay. So now let's assume that we are cutting the mass by any proportion and we are getting that, try to get the solution. Let's see how is it. So I am taking the mass, let's say this is alpha times m with the spring k, and this portion will be 1 minus alpha times m, because once it is lambda times m and it is 1 minus lambda times m, then you will repeat that. So this portion will be repeated. So here I will again have lambda times m k into again 1 minus lambda times m. So this portion will total become m. Make sense? So I can cut it with any value of lambda, and lambda must be this. Clear? No doubt on that. So if it is like that, so all of you agree with me that I can cut it like that? Agreed? Very good. So if I cut that way, what is the force balance diagram for that? We have to equate the forces. Now I cut that full thing and I take that thing out and I try to balance the forces. So let's try to do that. So if this is that lambda m and this is 1 minus lambda times m, now let's just apply the forces. I'm applying the two forces. Obviously the two forces should be opposite in direction, then only they will be in equilibrium. Okay, and what will happen additionally, if you think, once we will have that next unit, so that is my, let's say, nth unit, and this will be my n plus 1th unit. Then same, sorry, this is not F1 force, that force should be something different. Okay, just a minute, let me just first erase it. So let's assume that that is the nth cell. Okay, so I just cut that nth cell. So once I cut that nth cell, the left side force of the nth cell is Fn0. That 0 means left side, and then other side Fn1, that is the right side. Okay. Now, if you think that next unit, what will be the left side? Fn plus 1, 0 with the spring. This will be Fn plus 1, 1. Agreed? Now, and also, what are the displacements? This displacement will be y n0 and this displacement is yn1. This displacement will be yn plus 1 0 and this is yn plus 1 1, because here we have to think it always like left side right side, left side right side, this way. Okay, and now if we try to apply the Bloch theorem, because they are periodic, and what are the vectors associated here? The vectors associated here are Fn0, and what is the counterpart of the Fn0? Fn plus 1 0. So if you see, what will be the Bloch theorem for this case? Fn plus 1 0 will be equal to Fn0 into e to the power of I kappa I. Agreed? And what will be yn plus 1 0, that will be equal to yn0 into e to the power of minus I kappa I. Agreed? Agreed? All of you agree with me? Good. If you agreed, now think, so this is the Bloch theorem, and what can we get from this if we do the force balance? What can we get? So what will be the equation for this first portion? So this portion, if I write it, what happen? Lambda into m minus omega square into y 0n plus k into y 0n minus this equal to Fn0. Agreed? Anybody did not understood, please let me know. All of you got that? If I do this first balance, now I will do the next balance. So if I do the next balance, what can I get? Minus 1 minus m omega square y yn1 plus agreed? Agreed, all of you? Good. Okay, so you can see now that from this part we can able to write that, and we have also written the two Bloch theorems here. Okay, up to this all of you are okay with me? Very good. Now what can I do? What will be my target? So our target is to find out basically relationship between omega versus mu or k, whatever. Yeah. So now if you think these two relations we are getting. Now first thing what we can do, maybe we can add these two matrices. So if we add these two matrices, or okay, before we add that, now let's first try to understand what we are getting here and what the terms we need, what we do not need. Let's try to see. So here we can see we have yn0. Now you see yn0 is here, yn is here, and these other terms are not associated terms, they are separately terms. Then yn0, yn1, this and this. Now you see in this equation omega is here, we have omega, but what is missing? What is missing from here? Wave number. So kappa is missing from here. Now we have to put the kappa back. How can we do the? How can we make the kappa back? So we need to use that block theorem somewhere. Where can we use that block theorem? So let's try to think. So our target is what? These things are correlated, but we do not want these parameters. So what additionally we can write, that is the continuity equation. Continuity equation. So what is the continuity equation tells? Continuity equation tells that displacement, they are equal actually. If you see yn1 and yn plus 1 0, they are basically the same node. So their displacement is same, they are not different. Agreed? Very nice. So if they are equal, now you see what this relation tells. If I just substitute it back here, I can get it. So first one is from continuity and this one is from block. Agreed? I can write it, no doubt. Good. Next thing is the force balance. So where I do the force balance? I will do the force balance at this junction. So here what can I write? Fn1 is equal to Fn plus 1 0. You see, we have just cut it. So these two forces which are coming, they are opposite in direction and they are basically same. Exactly. Agreed, all of you? So that junction, once we are cutting it, they should always oppose each other. Important point, once we cut, as this is the same node, displacement should be same for both, but force will be opposing each other because it is cut. If you cut, shear force will also oppose, bending moment will also oppose, axial force will also oppose. Agreed, all of you? So that's why these force directions are opposing. Now if I think Fn1 is equal to Fn plus 1 equal to Fn1 plus 0. Now you think, what is the block theorem tells? Fn1 equal to Fn0 e to the power of minus IKA. Interesting. Yes, can I substitute it? Yes. So now let's see what our equations become. Minus lambda m omega square yn0 plus k into yn0 minus e to the power of minus IKA into yn0. Instead of yn0, I am writing that equal to Fn0. Agreed? All of you? Minus 1 minus lambda m omega square yn1. Instead of yn1, I am writing yn0 e to the power of minus IKA. You see? Yn1, we have already find it out. This is this. Plus k into yn1 again yn0 e to the power of minus ika minus yn0 equal to minus fn0 e to the power of minus ikn. Okay, so that's become my equation 1 and equation 2. So now what I will do, I will divide the equation 2 with e to the power of minus ika, because look, e to the power of minus ika seems like it is like quite taking the full thing, so I just divide it so that I will get rid of it. yn0 yn0 e to the power of ika equal to fn0 with a minus sign. That will be equation 3. Agreed? So that is e to the power of ika multiplication. Okay, so I just multiplying with e to the power of ika and I will get that solution. So now what happened? If I add equation 1 and 2, okay, see very carefully, these two terms are there which will get cancelled out. Now let's add them up. So add, what will happen? Look, here it is minus lambda m omega square, here it is 1 minus m, so it will become minus m omega square yn0, lambda goes, it gets cancelled out, plus k into 2 minus e to the power of minus ika minus e to the power of ika into yn0 equal to 0. Think, these and these get cancelled out. Okay, plus and minus. Here also if you see, this term become 2, this with a minus sign and this with a plus sign, minus sign. Done. All the things are added up. So what is your dispersion relationship become? Check the previous one. If we do that, both the things will give you the exactly same result. So it actually tells us very important point. You see, we got the exactly same relation here. So this tells us very clearly a point that wherever we cut, it hardly matters, we will get the same dispersion relationship. But this process is bit complicated, but this is very effective for the complicated systems. So otherwise we would have not done that, because for complicated systems, just putting the displacements will be very difficult to solve. Then often we can just identify what are the unit cells and implement this type of methods. Okay, is that clear? So you see, there is a 2 prime point. Whatever the way you do, Bloch theorem will be used, whatever the number of degree of freedom, twice the Bloch theorem will be used. If you see here, what is the degree of freedom for the Stark unit cell? 1. It is like mass and spring, so it's a single degree of freedom, and the connection is also single degree of freedom. How it is connecting with the other is also single degree of freedom. So once it is single degree of freedom, single Bloch theorem will be used twice. You may use it in the displacement domain, that point previous and that means the back and previous, that means the back and forth, both the side you can do it, like front and back, or you can take that unit cell and implement the Bloch theorem once in displacement and another in force. So you can think, if we are solving a beam, let's say like if we are doing a complex system like beam, let's say, which is, so how many degree of freedom are there in the junction? 2 degree of freedom. Displacement means transverse displacement and rotation. So we have to use 4 Bloch theorems, either in terms of displacements or in terms of forces. 2 in force, force means like force, bending moment and shear force, 2, and slope and deflection, 2, or 2 for slope, 2 for transverse displacement. So those actually started complicating the whole things. The beam is also not that big complication. Like you can see, like in the next class, we will do the generalized monocouple system. And then you will see that the generalized version of it, that is primarily like we developed that. One of our PhD student, Avigna, she is completed now. She primarily first put that concept like that. If can we have a generalized monocouple system so that internally there will be whatever the degree of freedom, but connection is with only a single degree of freedom. Then how the wave can able to propagate from one side to another side. Actually developed that full concept based on that. Okay, so that can able to tell us negative mass, negative stiffness, and so on. Different types of things can also be done from that. Okay, so with this, I would like to close it here. Thank you very much.